Section 2.8 is the derivative as a function. If you recall, in section 2.7, we defined the derivative at a real number a, and it looked exactly like this, except for we had the number a here, here, and here. In section 2.8, we replaced the number a with the variable x, and we think about the derivative as a function defined on various values of x as long as this limit is defined. So first we're going to look at the derivative in terms of graphs. So here I have a function, the graph of a function f, and I want to sketch the graph of the derivative of f. Just a basic sketch. The key idea is that the derivative is just giving me slopes of tangent lines to f. So I'm going to do just a very rough sketch. The first thing I do is I look at the graph of f and I look for the horizontal tangent lines. So I see 3 of them here. This tells me that the slope of the tangent line here is 0, which means that my derivative function must pass through 0. Same thing happens over here. The derivative function must pass through 0, and same thing over here. The next thing I take note of is the fact that on this interval over here, my function is increasing, so I know that the slopes of the tangent line are positive. So the graph of the derivative should be above the x-axis here. In this interval, this function is decreasing, so the slopes of the tangent line are negative. Therefore, the graph of the derivative should be below the x-axis. Again, we're increasing over here and decreasing over here. Another piece of information I have is that it appears that the slope of the tangent lines look like they're about equal to 1 over here. So I'm just going to plot a point going through the 1 here. And as we approach -1, they're getting flatter, okay? And then it looks like at 0, the slope of the tangent line is -1. So I'm just going to put a -1 down here. And over here again, it looks like the slope of the tangent line looks like it's around 1. Over here, it looks like the slope of the tangent line is about -1. That just gives me a little more detail. So if I want to do a quick sketch of my the graph of my function, the derivative function, it looks something like this. So this is f prime. So just to recap, if I'm given a function f and I want to sketch the graph of the derivative, just a very basic sketch, I look for the horizontal tangent lines, okay, because I know that those are the points where the derivative passes through the x-axis. And then I check and see where the function is increasing, decreasing, increasing, and decreasing. That tells me where my derivative is going to be positive or negative. Positive or negative. Next, if I want more detail, I try to look at specific point values of x and estimate the slope of the tangent line. That gives me a little more accuracy in the graph of my derivative. The next thing I want to do is use that original definition of the derivative to actually compute the derivative function. It's really not that different from what we did in section 2.7, except for now I have the variable x instead of having a number like 5. So here is my first example. we're going to use the definition of the derivative to compute the derivative function of f of x. Okay, so my derivative function is given by now I'm going to substitute these values. I have okay, if I try to let h go to 0, then this limit is indeterminate, so I need to do some algebra. The first thing I notice is that I've got these lots of fractions inside of fractions, so I'm going to try to clear those out. I'm going to multiply by the LCD of the denominators, these denominators, divided by itself, so this is just equal to 1. So that takes care of the numerator, and in the denominator I have this times this. Now I only have one fraction, but if I try to evaluate this by plugging in 0, I would still get 0 over 0. So one of the other techniques we used in section 2.3 was to multiply by conjugates, so I'm going to do that. I'm going to multiply by the conjugate of the numerator. Over itself. So that's just equal to 1. And this is just going to give me a difference of squares, this times this. So I have 81 times x minus 3 minus, and then this times this will give me 81 times x plus h minus 3, all over this very large expression. Okay. Now, in the numerator, if I simplify this a bit, I can see that I'm going to get 81x minus 243 minus 81x minus 81h plus 243. So that's what's going on in the numerator. And these terms are going to cancel, and I'll be left with I'll be left with the limit again, this is, going to be 0 over 0, but I can factor. I've got the common factor of h there. And when I try direct substitution after that, I get negative 81 over the square root of x plus 0 minus 3 times x minus 3 times 9 x minus 3 plus, kind of running out of space here, plus 9 x plus 0 minus 3. And that's going to simplify to negative 81 over, this will give me x minus 3, this root times the root, and then I have times 18 x minus 3 given by these two terms. I can divide this by 9, right? And I get negative 9 over 2. So my final answer is going to be negative 9 over 2. This times this will give me x minus 3 to the 3 halves. And this is my derivative function. So this is f prime of x. Okay, so that's an example of how to use the definition of the derivative to find the derivative.